CF for introduction. So can you confirm me that you can see my screen?
Yes.
Okay, great. So yeah, today's our talk is about a likelihood-free nonlinear filtering approach using machine learning-based approximation of conditional expectation. And this is a joint work with Professors Sebastian Krumschei, Herman Martis, and Raoul Tempon. Okay. So the topic of our talk is in the framework of data assimilation. So data assimilation is a set of techniques that combine measurement with numerical dynamical model to infer the states of systems, dynamical system under presence of uncertainties. And this framework has a wide range of applications, for example, climate or weather forecast, geophysics, nowadays in constructing digital twins or doing structural health monitoring. Filtering is a particular techniques in that data assimilation framework, and usually they have two steps. Could you confirm me that you can see the mouse?
Yes.
Okay, great. So in filtering methods, we have two steps: forecast and update. In the forecast, we use our dynamical model to give some forecast of the system at time tk plus 1 given the state at time tk. This forecast usually has a significant uncertainty, and in the update step, we combine the observed data with the forecast to obtain some updated description of the state, which can have a reduced uncertainties compared to the forecast one. Ensemble Kalman filters is a very popular method in filtering for filtering, because it can be implemented quite straightforward. The updating maps here is linear, but because of that linear maps, for nonlinear dynamic with long observation time, the performance can be degraded. So our aims is to develop ensemble conditional mean filter with construct based on the conditional means and using the projection methods. It's important here to use projection methods because in this approach, the filter updates can be split in two terms: the Kalman filter, which in linear term, and a nonlinear update. This split give the filter many advantage. For example, it inherits the good performance of ML-EnCMF for closely linear Gaussian setting, and for nonlinear setting with the nonlinear updates, we can correct the bias, and we can also reduce the variance error. And in particular, this approach can be implemented straightforwardly on top of the ensemble Kalman filter. So before going to talk about the conditional mean filter, let's recall the setting of the Discrete-time filtering approach. Here I denote capital QK as the random variable represent the uncertainties of the dynamical system as observational time TKs. It means that at time TKs, we obtain some observation data, and the observation data I denote as the y hat k. We assume that the observation model is known and denoted at h, and we also model the measurement error as a random variable called psi k here. Then in this setting, the measurement data can be considered as a sample of the random variable yk. Okay, and if we make the assumption that the random variable qk is a Markov process, and also ck are statistical independent and also independent with respect to qk, then we can update the conditional densities of qk given measurement data up to the time tk using Bayes' rule. In particular, the priors is the conditional density of qk given the measurement data up to the time tk minus 1, and the likelihood is obtained by the measurement as the time tk. And beyond these observations, filtering methods try to approximate the Bayesian update, because we know that in high dimension settings, solving directly the Bayes formulations is not easy. It's computational expensive and even prohibited. So filtering methods in the forecast step, we start with the update random variable from previous time step, which is tk minus 1. We use our dynamical model to obtain the forecast state denoted as qf at case, and we also can evaluate some characteristics or some sample of the forecast of measurement random variable denoted as yfk here. In the update step, we try to construct a filtering map denoted as T here that map our forecast information conditions on the actual measurement data, and we obtain the update random variable. And the map here is identifies as the probabilities of this random variable approximate well the posterior density in some criterion. And if we use the map taus as a linear function, then we obtain the formulation of Kalman filter, which say the updates of the updates random variable is equal to forecast random variable plus the difference between the forecast measurement random variable and the actual measurement data multiply with a metric case, which is the Kalman gain. And from this formulation, if we write down the mean and the covariance of matrix QA here, then we can obtain the usual formulation of Kalman filter. And if we use the ensemble technique, that's it, we use ensemble of samples to represent the random variable QA, QF, SYF, YF, then we obtained the ensemble Kalman filter. And because it's linear updating here, so in closely linear Gaussian setting, usually ensemble Kalman filter have very good performance. On the other hand, the performance is degraded when we have nonlinear dynamic and long observation time. And that's motivated to improve the filter by using conditional expectation. And we, in this section, we will talk about this filter in details. Furthermore, in our setting, what is the conditional mean that we talk about? The conditional means of random variable QF given YF is sigma YF measurable random variable, so that for any measurable set A in the sigma algebra, then its measure under unconditional random variable is equal to its measure under the probabilities of the conditional random variable. If we assume that the the random variable YF, QF, and C are continuous random variable, then we can define it via the posterior means. It says that the conditional expectation or conditional mean in this case in particular as a value y is equal to the posterior means given value y. And there are two important properties of conditional means. The first property says the expectations of the conditional means is equal to the expectation of the unconditional variable. And the second is the law of total variance, says the covariance of the unconditional random variable can split into the expectation of conditional covariance plus covariance of the conditional expectation. So it's here we see that to compute the expectation of conditional variance, we just need to know the prior variant which usually available and the covariance of the conditional means. So yeah, we will use this property to analyze our filter in next slides. So from previous slide, one can say that okay, to compute the conditional means, we can use the Bayes rule, but it will require to sample the posterior density, and it's not a good approach. Instead, here we will use the orthogonal projection properties of conditional mean to approximate the conditional means later on in the future. So according to the Dubh-Deakins lemma, because the conditional means is a sigma YF measurable random variable, so it can be expressed as a composition map phi applied on the random variable YF. And the map phi here satisfy the condition of minimum mean square error. That means that the map phi minimize the expected value of L2 norm between forecast random variable and the map phi applied on the measurement random variable. Okay, and here is one interesting thing. If we approximate the map phi at a linear function, a YF plus b, and solve those problems, then we have a is nothing else but the Kalman gain. And yeah, of course, if we plug again, yeah, I will talk about it later here. Okay, now here I show you what the conditional mean filter is. The updated random variables is equal to forecast minus the conditional mean. Here is the conditional mean, and the conditional mean evaluates as the measurement data. And when we use the linear approximation of the map phi here, then we obtain the Kalman filter. So is this conditional mean filter is consistent with the Kalman filter. There are two important properties of conditional mean filter. The first one says the means of the updated random variables is equal to phi at y hat, and phi at y hat is actually the posterior mean. And to prove that, we just need to use the law of total means. Another property is the variance of this one. The covariance of this one is actually the effective conditional covariance. So the property B say that okay, the variance of QA is not exactly the posterior variant, but it has some nice property, and we expect that with that property, the error in terms of variance is reduced in comparison with the ENKF. And we can also say, okay, then we make some update here, but it happens only if the expectation of the conditional variance is much smaller than the variance of the forecast. Yeah. In comparison with the ENKF, ENKF do not have these two properties. So these two properties is really significant, because it say it not it say that we have the correct means, and we also have some nice idea, some nice property about the variance. In the next slide, I will show you some example to illustrate the conditional mean filter. One is a supportive example, and the other one is a counter example. Here we start with a supportive example. We assume that the observation map here is equal to Q if Q is negative and Q squared if Q is positive. We also assume that the forecast is a Gaussian, and the measurement is also a Gaussian. Measurement error is also a Gaussian. That in this figure, I show you the conditional means in blue, and what happened when we use a Kalman filter to approximate the conditional mean. So it will be a linear function, and you can see that it have a lot. It have a big bias. It have a big bias. Yeah. Okay. In the right figure, I show you the CDF of the conditional variance. So the conditional variance as at a random variable is have certain distribution, and in this case, the conditional variance is bounded somewhere close to 0 to 0.25. And when we use the ensemble conditional mean filter, the variance is somewhere here is about 0.17. But if we use the ensemble Kalman filter, then we obtain the variance is here. So it's out of the range of the conditional variance. Okay. Here the figure of the density function. We have here density function of the ENKF. Here is our filter, and those dashed lines in PDF of the Bayesian posterior. So our filter does not approximate well the Bayesian posterior, but it's much better than the ENKF. And the mean values of our filter and Bayesian posterior are identical, as expected. Okay, now we go with a design counter example. In this example, everything is the same, except that the map HQ is equal to Q squared. And in this setting, the Bayesian posteriors have two symmetric mode. And if we have the true values, for example, close to 10, then these two modes will concentrate it as -10 and 10. Okay. In this case, our filter ENKF, our filter ENCMS and ENKF are identical, and moreover, they are also identical to prior, so they do not make any updating. But this design counter example have some very special properties. When we look at the distribution of conditional variance, is some point when the true value close to 0, then the variance is close to 0, but it can grow very large. For example, if it's 40, it means that it's like 10 times the prior variance. So if we are stand from the point of view of experimental design such measurement map. And actually when we compare the expected conditional variance in this example is 4 and is equal to the prior variance also. In previous example, the expected conditional variance is much reduced compared to prior variance. Okay. Yeah. So in the next slides, I will talk about how we implement the ensemble conditional mean filter by coupling machine learning and ensemble technique. So to implement the ensemble conditional mean filter, we have two approach at least. The first one is to use the likelihood-based approach to approximate the conditional mean, but it will be prone to error for small ensemble size and can cause the filter diversion. And in practice, the ensemble size are usually small. So we want to avoid that, and we will use the orthogonal projection to approximate the conditional mean. In particular, we approximate the conditional means as the sum of a linear maps and a neural network here, and the linear map here coming from the ensemble Kalman filter. And applying the orthogonal projection, we can solve for the hyperparameter of the ANNs by solving the mean square error problem here. So how this idea can be coupled with the ensemble technique? In the ML-EnCMF, we still have the forecast step and update step as the ML-EnCMF, and in the forecast step, we can obtain the ensembles of the state random variable and the ensemble of the measurement random variable. In the update step, we still estimate the Kalman gain, but then in the next step, we solve the minimized mean square error problems using the forecast ensemble as the training data. So it's right in here the error. After obtaining the ANNs, we plug into our ensemble conditional mean filter, and we can evaluate the update ensemble with this formulation. And the first pass is identical to the ensemble Kalman filter. This is the nonlinear term used to correct the ENCF. Okay, there are three important procedures we implemented to make the filter stable and avoid diversion. They are data augmentation, model selections, and localized or Sparse ANN that I will explain in the next slides. Okay, data augmentation. The idea is we can sampling at a very low cost the random variable seeds of measurement error, and then we can take this advantage to build a control variable estimator instead of the crude Monte Carlo estimator. And in terms of formulation for each forecast sample, here we can generate a lot of measurement error, and it's straightforward to show that the statistical error of this control variable estimators is much smaller than the Monte Carlo estimator. Model selections. Yeah, because we do updatings for many steps, and there are maybe some steps that the settings is closely Gaussian linear setting. So by introduce the nonlinear terms in the ML-EnCMF can bring some some error, and the performance may be not as good as ENCMF. So the idea here is that we can select the ENCMF or ENCMF for each component of the updated vector QA. To do so, we compute the mean square error of the linear approximation of conditional means and mean square errors of nonlinear approximation of conditional mean. Then we identify a vector A, so that the component A alpha is equal to 1 if the nonlinear approximation shows smaller error, and then we can plug it into our updating map. So it means that there are many updating steps, and at some updating steps, we can use 100% with the ENCMF, another 100% with ENCMF, or something between, depending on the vector A alpha here. Okay, the test procedure we use a localized or Sparse ANN structure. The motivation behind is does think about the vector Q here. It can be a vector or it can be a few, and the two components may have negligible correlation or no correlation at all if their spatial distance is really large. So we want to translate this observation into the constructions of the ANN. Let's take one hidden ANN, for example. It's given here. It's mapped a vector Y to a vector Q, and W1 and W2 are the matrix of weight, and gamma 1 and gamma 2 are the bias. And sigma, of course, is an activation function. So instead of use dense matrix W here, we enforce that W alpha primes is equal to 0 if the distance is bigger than certain limits called Li here. And it means that the matrix, the weight matrix are sparse. And it brings many benefits. For example, it's avoiding the overfitting in terms of correlation when between spatially far component. In addition, because it is sparse, so we can compute it faster, and we can also reduce the number of hypermeter required to be trained. Okay, now I will use the developed filter for tracking the Lorentz system, which is an experiment that's common due to evaluate the performance of the filtering methods. We will see two examples, Lorentz 63 and Lorentz 96. Okay, Lorentz 63 models is a system of 3 ODE, and we choose the parameter of the ODE so that the dynamical behaviors in a chaotic regime. We use an identical observation model with some added noise, and the noise is a Gaussian, follow Gaussian distribution, and the observation times is equal to 1. Okay, we use 2 hidden layers, dense ANNs with 20 nodes at each layer, and this figure shows the root mean square error of the approximation of conditional mean using our methods here and using the likelihood approach. As you can see that using our methods, the error is significantly smaller, in particular for small ensemble size. And this is an advantage of the machine learning ensemble conditional mean filter in practice. For the big ensemble size, the the difference is reduced as a practice because there are just two different methods to approximate the same thing. Okay, this table show the performance indicators in terms of the average root mean square error. It means that they compare the ensemble mean and the ground truth. And we also report the average coverage probability, which estimates how many times the ground truth falling in the 95% confidence range. And we do it with different size of ensemble, 20 to 200. We compare our machine learning ensemble conditional mean filter with the ENKF and also with the likelihood-based approach for implementing the ensemble conditional mean filter. Okay, let's compare ML-EnCMF and ENKF. So for every reported ensemble size, our filters outperform the ENKF. For in particular, if some ensemble size 200, then the reduction in terms of mean square errors is up to 30%. In comparison with LL's ENCF, our methods have much small error for small ensemble size. And for bigger ensemble size, again, they are almost identical. For likelihood-based approach, we also remark that when the ensemble size is small, it's even even ENKF outperform the likelihood ensemble conditional mean filter. Okay, now we move to a more complicated example in tracking low-rank 96 system. So low-rank 96 systems is ODEs over a periodic domains with 40-dimensional state vector. And again, we choose the force here equal to A, and is ensure that the dynamical behavior is in chaotic regime. Instead of use a full observation model, we assume that we can observe only half of the state, and the noise here is still following a Gaussian distribution. We take the observation time equal to 0.4, which is comparable to 48 hours in the weather forecast model. To implement the ensemble conditional mean filter, we use one hidden layer ANN with 40 nodes, and we use also localization. And by using localizations, the number of training weights is reduced almost by 6 times, from 2,400 trainable weight to 420 trainable weights. Again, here is the table of performance indicator in comparison of the among three filter for different ensemble size. And we observe the similar pattern. Our filters is always better than ENKF. And the reduce in sum of root mean square error is up to 20%. In comparison with the likelihood-based approach, the machine learning-based approach outperform for small ensemble size. For example, here, for large ensemble size, the machine learning approach and likelihood approach are identical. Okay, so in conclusion, we developed a machine learning-based ensemble conditional mean filter via orthogonal projection. The filters inherits the good performance of the ENKF for closely linear Gaussian setting. moreover, the filter updated means marked as a posterior, and the filter updated covariance coincide with the expected conditional variance, and therefore the error in terms of covariance is expected to be small. And we saw that our filter have significant improvement compared to the other methods such as ML-EnCMF and likelihood approach for implementing the ensemble conditional mean filter, particularly for small ensemble size. Last but not least, there are still work to do for example, to correcting the covariance or higher orders moments. So many technical aspects of this talk is reported in this paper. And with this, I thanks for your attention. Thank you.